in this video, I'm going to say a few words about motion, about position, velocity, acceleration, speed, the tangential and normal components of acceleration, just to wrap up our unit on vector valued functions. So first I want to start out talking about an object that's traveling with a constant speed. So, I've got some kind of object here. It's got a velocity vector. And we'll just say, suppose that its speed is constant. Okay. So last time I showed you that if a vector valued function was constant, then its derivative was orthogonal to it. Then they dotted to 0. So what I'm saying is, if the length of v is constant, then v is going to be perpendicular to v prime, or orthogonal. And we say that by saying that their dot product is 0. Now we also know from, Cal 1, AP Calculus, whatever, that v prime, that's the acceleration vector. Okay? And in terms of the motion of the object, that kind of makes sense, because I'm going to just kind of draw in a line here, dotted line, kind of at a right angle to the velocity vector. But if the acceleration vector was basically not on this dotted line, you could envision it as pushing the object to have more speed, or pulling against it and slowing it down. And so I'll have a little bit more to say about speeding up and slowing down. So basically what I'm saying here is that v dotted with a has to be 0, which means that v is perpendicular or orthogonal to a. Okay? So what I'm saying here is that in order for the speed to be constant, the acceleration vector is either going to have to be right there, or maybe down here. Okay? Because again, if the acceleration vector were out here, it would be, we know that acceleration is related to force. I'm not a physics teacher, but even I know that. And so you can envision it as pushing the object, and it's going to increase its speed. And if the vector was back here, that's going to also decrease its speed. And so we're going to formalize that here, say right now. Okay, so I think I'm going to just kind of, reproduce this drawing a little bit out here, so I can, draw you a couple of cases. So, again, same object, same velocity vector, and, I see that's right in the glare spot, but it'll be right. Envision that being orthogonal. And what I'm saying is that if you had an acceleration vector that was, say, out here, then, there would be at least part of this is going to be going in the direction of velocity. And it would make sense to me, or I think it would make sense to you as well, that if the acceleration vector was more or less in the direction of the velocity vector, then the length of the velocity vector would increase. And I'll just, call that A1. And then if the velocity vector was back here, or in the most extreme, the acceleration vector, in the most extreme case, if the acceleration vector was straight back here, well, that would just be pulling all the way against the motion of the object. Over here, if the acceleration vector is this way, we know that, it's going to be speeding up, but the path of the object is also going to be turning a little bit towards that. And I'll have more to say about that in a few minutes. And so I was going to, just draw, maybe A2's down there, opposite the direction of motion. Okay? And what I'm going to tell you is that if the dot product of v and a is positive, then the speed will be increasing. But we know from linear algebra, or maybe pre-calculus if you really intensely studied vectors, that because of the cosine property, this is the same as saying that the angle between v and a is acute. If the dot product is positive, that means that the angle between the two vectors is less than 90 degrees. Okay, so but I see that right here, the angle between the two is less than 90 degrees. So this is confirming what I had suspected. And then I can say the opposite as well, is that if v dotted with a is negative, then I know that there's an obtuse angle between v and a, and I know in some sense the acceleration vector is moving in the opposite direction of velocity. Okay, so then length of v is decreasing. And I feel like I had something else to say about this, but oh yeah. The connection to AP Calculus, I had suspected this for a while, but this, motion has never really been a focus of my multivariable calculus course. We look at the curves, right? And I leave the actual motion and things like that to our physics class. But in AP Calculus, we had said, I'll switch colors, give you a little flashback. We had said that for, especially in, I guess we didn't really talk about speed increasing or decreasing when we looked at parametric equations, but for the, motion along a straight line where velocity was a function of time, acceleration is a function of time, it's all just a, real value function. We said that, if v and a had the same sign, then speed was increasing. Well, that kind of makes sense because, on the same level as this, because if v and a have the same sign, then the product of v and a will be positive. Okay, so I'm going to say, also v times a is greater than 0. Okay? Now, times is kind of taking on a different meaning here, right? We're just multiplying two numbers as opposed to dotting two vectors, but, it's the same symbol, and it's kind of the same idea. And so I'm thinking, in future years, this is going to be the condition I'm going to use in AP Calculus, for all the people that are going to go on to multivariable calculus. So it seems familiar, like, oh yeah, I remember multiplying v and a and seeing if it was positive or negative. And I think it's somehow, better than same sign, different sign. I don't know, there's something about that always kind of made me suspicious. So if v and a were opposite signs, well, that meant that in our class, v was, the length of v was decreasing, or pardon me, the absolute value of v was decreasing, the speed was decreasing. And I always just kind of draw pictures of the graph of the velocity and say, well, speed is the absolute value, and if it's, if the graph of velocity is going away from the time axis, then speed would increase, and that's going to be where they have the same sign, like positive and increasing or negative and decreasing. And if they had opposite signs, well, then the speed would be decreasing because the speed, the absolute value of velocity, would be going closer to 0. It's either positive and decreasing or negative and increasing. So, I'm going to say that v times a in this sense is less than 0. Just to kind of tie this back to what we did last year in AP Calculus. All right, so I started talking about, what happens when the speed of an object is constant, and then I talked about, speeding up and slowing down, and that was really kind of an aside to tie something into AP Calculus from last year. But now I want to talk about, if the speed is variable with respect to time. And so one thing that I'm going to prove for you that is really, the more you think about it, is not trivial, is that if we've got, some kind of smooth curve, and we've got a position function, and we've got a unit normal that's existing everywhere, then it's going to be the case that the acceleration vector for this object lies in the plane spanned by the unit tangent and the unit normal. Okay, so then A is an element of the span of the unit tangent vector and the unit normal vector at that particular time. Probably this should say A of t is an element of the span of t and n of t at, a given time. But you see what I'm saying. Okay, so I'm going to prove this for you. And, if you are not in my linear algebra class, that does happen occasionally. I get some people that just take the multivariable class. By the span, I should probably describe what I mean by the span of t and n. So I'm going to say that, last time we showed that t and n were orthogonal to each other, but it doesn't even really matter. Maybe I'll just draw you the picture of the span of two vectors in general. Suppose this is v and this is w. Okay. Necessarily, this is going to kind of imply a plane, and that's what we mean by span, is that it kind of, anything in, that's not the best parallelogram I've ever drawn, but, anything in this plane is in the span. And so what we would do is, we'd say that this vector A is in the span. If we extended the parallelogram a little bit, which I would do if I had, more space or was drawing better, we could say that, some things down here, those are also going to be in the span of v and w. The big thing is that if something is in the span of two vectors, then we can write it as a linear combination. We can, we're going to be able to write our acceleration vector as some number of t's plus some number of n's. Okay, and so we can make up our acceleration vector entirely out of t and n. And so I'll have, have a little more to say about that. But first I'm going to prove to you this. Okay. So first I'm going to start off with, reminding you what t is, right? It's the unit tangent vector. Okay, so remember that t is the unit tangent. Okay, so it's the derivative of r divided by the length of the derivative of r to make it a unit vector. Okay. Now, for this situation, I'm interested in talking about the acceleration vector of an object moving along a curve. So the derivative of r is going to be something that we interpret as velocity. Okay, so this is the velocity vector made into a unit vector. Okay. But this means that, well, I could really just say that the velocity vector is the unit tangent scaled up by the speed, right? Because this is the speed, the length of the velocity vector. And so that means that v is going to be t scaled up by the length of v. Okay? And if two things are equal, then their derivatives will be equal. So I'm going to say that the acceleration vector is the derivative of the velocity vector, which is going to be the derivative of this thing. And now, this is the type of thing that you look at it, and it's the length of a vector, so you think, oh, that's a number. And you might be tempted into thinking, oh, that's a constant, so I can just, kind of factor it out and take the derivative of t, and then put it back in after I took the derivative. But this is variable with respect to time, right? Because I was saying that this is a situation where the speed could be variable. And so I'm going to need to observe the product rule. And so I'll have, I'll take the derivative of this thing first, and this is a real valued function. So it's probably going to involve a square root. Okay, oftentimes it could be unpleasant. But it's going to be the derivative with respect to time of the length of v, or the speed. And then we'll leave t the same. And then I'll add in, okay, leaving this thing the same, the derivative of t. Okay. Okay, now, I think this was in the last video, or maybe it was in the last time we met, we said that the derivative of t was somehow related to n, okay, the normal vector. So what I'm going to do is I'm going to multiply this thing by a clever form of 1. Okay, I'm going to multiply it on top and bottom by, in fact, I'll even use a different color for that. I'm going to multiply this thing on top and bottom by the length of t prime. So I'm just multiplying by 1. So I'm not changing this. So this is length of t prime divided by length of t prime. So I haven't changed it. But then what I'm going to do is I'm going to put these two together. T prime divided by the length of t prime, that's the unit normal vector. So I'm going to say that this is equal to derivative with respect to time of the absolute value of v, the derivative of speed times t plus, and then now what I'm going to do is I'm going to kind of shift this around, and I'm going to say length of v, length of t prime. Okay. But then I'll have t prime over the length of t prime. That's the unit normal vector. That's the definition of n. Right? And so now I'm going to say, I'm going to just define, let AT equal the derivative of speed. And AN be this product here, this speed times the length of t prime. Okay. I am asking you to note that both of these are real numbers, a sub t and a sub n. Okay. So I'm going to say note AT and AN are elements of the reals. Okay? They're lengths of vectors. They're the derivative of a length of a vector. The derivative of a real valued function will certainly be real valued. And so I can say, this line, this is still equal to A. So therefore, I can say that A is equal to AT multiplied by unit tangent plus AN multiplied by the unit normal, which is to say that A is a linear combination of T and N, which is what I set out to show in the first place, that A is in the span of T and N. Okay, so it's just in the plane that's generated by those two vectors. All right, and the last thing I've got for you in this video is I want to, show you some other ways of computing the tangential and normal components of acceleration. So we're going to just take these as the definition of tangential and normal component of acceleration, just what we had as our kind of factors of our linear combination. The derivative of speed is the tangential component of acceleration, and the speed multiplied by the length of t prime is going to be the normal component of acceleration. But I think I'm going to be able to draw you a picture that would help you understand, a couple of other ways that we could compute this. And let's see. Oh, okay. So I'm going to say I've got a space curve, and I need to draw this carefully. So I'm going to go. I've got a space curve right here. Okay, and suppose that I've got, a point of tangency right about here that I'm interested in. Okay, we know that the velocity vector and the unit tangent are going to point, in the direction of motion. So I'm going to say that. And I also know that the normal vector is going to be orthogonal to the unit tangent vector, the unit normal, and it will kind of go in the direction that we're turning. So it's going to go this way, and it's going to have the same length. Okay, so hopefully that's about right. And what I'm going to do is I'm going to say, basically suppose that the acceleration in this situation, if the thing was really slowing down, suppose that the acceleration vector was, back here. That would be entirely possible. In this case, the velocity vector is heading this way because the orientation of the curve goes up the way I drew it. Well, then the object would be slowing down along its path. Okay? And moreover, I think what I'm going to do is, I'm going to just kind of, I think I want to make my acceleration vector a little longer, just kind of a proof point. And I'm going to put it out here. And then what I'm going to do, I just drew this at kind of too much of an angle, I think, is I'm going to show you this the plane spanned by t and n. Except in this case, since the acceleration is kind of going the opposite direction of motion, I'm going to have to extend. Okay, probably, maybe I should have drawn the parallelogram first. That's pretty decent. I guess it's not only a parallelogram, it needs to be a rectangle because of the fact that t and n are orthogonal to each other. But you can kind of see what I'm getting at here. Maybe I'll even just redraw my acceleration vector. Live and learn. If I have to do it again in the future, I will draw the box first. And so it's going to be straight to there. Okay, and so what you can say pretty easily is that this thing right here, this is the normal component of acceleration, and this is the tangential component of acceleration. And one thing, and you can see that it's clearly related to the projection of a vector. And what I'm going to do is I'm going to say that, yeah, basically, if you're projecting onto a unit vector, then the length of that projection is going to be the dot product of the two vectors. And I'm going to leave that to be something you can verify on your own. But this length here, this is AN, and it's also the value, it's A dotted with N. And you could think about, if you go and look at the projection formula, it's going to have to do with the length of the one that you're projecting onto. But that's kind of it. I'll let you, we've talked about that before. And then over here, it's the same thing. This is going to be, the tangential component of acceleration is going to be A dotted with T. In this case, that dot product is going to be negative because they're at an obtuse angle. And I need to pause the recording for a second because I got people at my door. So now we have evidence to believe that this is equal to A dotted with T. And that this is equal to A dotted with N. Okay. And but these are not going to necessarily be the formulas that you're going to want to work with because, T and N can be a little unpleasant to find. If we already have them sitting around because, I don't know, somewhere along the way we computed them, I don't know what we were going to do with them, I suppose it's a multi-part problem. We could use that. But one thing I'm also going to point out is that T is going to be the unit vector in the direction of V. So I could say that this is going to be equal to A dotted with V divided by the length of V. Because of the way the dot product commutes associates all that stuff. And making sure that that's exactly what I wanted to say. Yeah, okay, on my note sheet I had said V dotted with A divided by the length of V, but that's the same thing again because the dot product commutes. And then the last thing, and I'm not going to prove this one for you, this is one that if you wanted to investigate on your own, this is one you could definitely run down. It's right at your level. I'm going to tell you that this is also equal to the length of the cross product of R prime and R double prime divided by the length of R prime. Or the length of the cross product of V and A divided by the length of V, or the speed. But I'm not going to write that down. I think you know that's the same. I'm also going to mention, and not even write down, and I had never known this. I just saw this mentioned in passing on an internet website. I was just browsing looking for an example. And by the way, I'm not going to do any examples in this video because I didn't find one that worked out anything less than really bad. And I'm already at 23 minutes, so I don't really think I want to make this a 30, 40-minute video. I'm just going to mention that the normal component of acceleration is equal to the product of the curvature and the square of the speed. Okay? I'm not entirely, I can see how it would be related, but that's just something I'm going to throw out there. I believe it's probably the signed curvature, but I didn't read deep enough. But these are the formula for the tangential and normal components of acceleration. That's what we've got going on here. I think that my drawing didn't go so well the first time, but you can envision, I'm going to just go for it. I don't care. Suppose we had a situation where the acceleration was in the direction of motion. So we had, T here, N over here, suppose they're a right angle, and maybe the acceleration vector is, I don't know, maybe it's really accelerating. Maybe it's huge. Oh, that was a mistake, right? I needed to go not quite so far. And then, I made that in blue last time. All right. Okay, and then again, this is the path of the curve. I'm gonna actually cut that off.
Good morning, students and staff. It's time.
All right, so I'm really not sure where I had left off when they started making their announcements or whatever, but what I'm going to say is that, the path of the curve had been over here, but I erased it because it was kind of in the way. But if the acceleration vector is in the direction of motion, then, I'm saying that we're going to be speeding up. But we're also, I'm going to say that this length here, again, is the normal component of acceleration. And this length here is the tangential component of acceleration. And in this case, AT is going to be positive, whereas in this case, AT is going to be negative. Okay, so if you were able to find out that the tangential component of acceleration was negative, you would know that the thing was slowing down, okay, for reasons that I had mentioned earlier. I think that's all I've got to say on this video. Come back for more on actual multivariable functions.